So in today's class, let's finish forward kinematics. Okay. So what is forward kinematics? So kinematics. So for an example, you have a robot and you are given some joint angles. So given the joint angles, find the position of the end effector. What does that mean? There are two types of joints in robot. One is a revolute joint. So you have a revolute joint, which is also the hinge, which is denoted something like this. And what you have is a prismatic joint. So which is like a cylinder piston. So that is actually shown something like this. And depending upon whether you have motion in X, Y, and Z, what we do is we add something like this. What does that mean is you have this piston cylinder type of assembly in horizontal direction, or you have translation in the horizontal direction. If I draw a line vertically, then you will have the direction in the vertical direction. So you can have three-dimensional motion. Now this revolute joint has an axis of revolution. So what I'm going to say is this is also called as R and this is called as P. That is how the robots are denoted. So if you have one revolute joint and one prismatic joint, that robot is RP. If you have two revolute joints, then it would be RR. If you have three revolute joints, it will be RRR. So let me give you a mechanism, and let's, for the sake of discussion, assume that's a robot. And this mechanism, what I want to talk about is this slider crank mechanism, wherein you have a crank, which is a revolute joint. There is another hinge, which is the revolute joint, and then you have a piston or the prismatic joint. And what I'm going to do is I'm going to draw a horizontal line, something like this. So if I were to call this a robot, this is going to be my RRP robot. Now, the most important thing for a robot is this concept of mechanism. Now, what is a mechanism? Mechanism is the soul of the machine. Now, so behind every machine, there is a mechanism. For an example, the simple lever that we have is a mechanism. It's actually a machine. Probably when you took statics class, the lever comes under the chapter simple machines. So there is a mechanism that captures the soul of the machine. Without a mechanism, machine cannot exist. Now, what is unique about this concept of machine? The concept of machine is for one unique input, you are going to have one unique output. Once again, for unique input, you're going to have a unique output. In other words, in kinematics term, the machine has a single degree of freedom. So what is the degree of freedom? Degree of freedom is the number of independent coordinates that are required to specify the state of the system completely. For example, I have an object. If this object is in three-dimensional space, it has 6 degrees of freedom. Translation in X, translation in Y, translation in Z, rotation about X, rotation about Y, and rotation about Z. But what you do is you add constraints and then basically take away those degrees of freedom. Everyone understood this? So for an example, when I was single, I had lot of degrees of freedom. When I got married, my degrees of freedom came down. Then I had kids, then I had degrees of freedom coming down. We had our second kid, now I'm an over constrained system. So basically, I can't do a thing that I want to do. So that is fact of life. Anyway, so you have this RRP type of mechanism. So what I want to do is I want to look at the forward kinematics. What that forward kinematics means is this. If I give you the link length L1, if I give you the link length L2, end effector is something at the end. It could be a probe, it could be a lamp, it could be a light, it could be a gripper, it could be a maybe just electromagnet, whatever. So this is the end effector. End effector. And now if I were to give you these angles, theta 1, and what I'm going to do is I'm going to give you this angle, and I'll tell you the reason why. This angle, theta 2. If I give you theta 1 and theta 2, please understand, you can tell me the position of this end effector. And the position of this end effector is going to be L1 cosine theta 1, L1 cosine theta 1. So remember, C theta 1 is cosine theta 1. And this distance, actually, let me be more clear. This distance is going to be L2 cosine 2. So this distance, if you were to look at, is L2 cosine 2, theta 2. So L2 cosine theta 2. Yeah. He has to wait. He's late. Now he has to wait. I'm not going to admit late students, because otherwise half of my time goes on checking who is in the waiting room and allowing them to enter. So too bad. So L1, L2. So this distance is L1 cosine theta 1 plus L2 cosine theta 2. Everyone understood this? Now, there are multiple ways of looking at this problem. Please understand, this distance O, A, B, and this from O to B. O to B is actually a vector. What do I mean by vector? As theta 1 and theta 2 change, this length OB changes. Do you agree with me? In this particular case, we know the direction. So for an example, if my theta 1 and theta 2 are going the same direction, then my OB would keep on increasing. If I reverse the direction, and I tell you what I mean by reverse the direction, then OB would be decreasing. This is super duper important concept, because all these quantities like for an example, theta, which is angular displacement, theta, then OB, which is the linear displacement. Those are all vector quantities. When you are defining a vector, you have to have the reference frame. A vector cannot exist without a reference frame. You need a reference frame. And what we do is we use a coordinate frame, which is a right-handed coordinate system. And that is all we are going to use in robotics 1 and robotics 2. And this is a triad. So, and again, it may be easier in this case because everything is planar. But once you start looking at the spatial mechanisms, then the things are going to be complex. So remember this. This will save you a lot of headache later. So right hand is like make this shape. This is X, Y, and this is Z. So for an example, this is X, this is Y, and Z is coming out. Don't use left-hand coordinate system. Everything will be opposite. Now, so if you have motion about positive x-axis, that motion is positive. So motion in this direction is positive. If you have motion about positive y-axis, that motion is going to be positive. And please understand, this is positive z-axis. Everyone understood this? How do we determine the orientations? So to determine orientations, curl your right hand, curl your fingers, and see where the thumb is pointing. If the thumb is pointing toward positive x, positive y, or positive z, then that rotation is positive. What that means is curl your fingers in the direction of x. This is positive rotation. Curl your rotation about y. This is positive rotation. Curl your fingers about z, and this is positive rotation. Everyone understood this? Remember, this will save you a lot of headaches in robot kinematics because you will have to assign the coordinate systems. You will have to assign the rotation directions. So now what I'm going to do is I'm given this mechanism or sort of this simple robot. This robot is RRP robot, and I want to assign a coordinate system. How do I assign the coordinate system to this RRP robot? The best thing is start with the first joint. Start with the easiest stuff. I'm going to call this X. I'm going to call this Y. Clearly, my Z is coming out like this. Do you agree with me? Next, assign. So every joint, you must assign a coordinate system. What that means is if I go to the second joint, this is how this is going to be. Again, this is X, this is Y, this is Z. Again, here, this is X, this is Y, this is Z. Some of you may ask me, do these coordinate systems, should they be aligned? There is no reason that they should be aligned. I mean, if you want to go crazy, you can orient the coordinate system however you want. But why to make our life complex? As far as possible, try to align those coordinate systems in the static equilibrium position. So basically right now, nothing is moving. So I would try to align the coordinate system in this particular case. And the biggest advantage of that is, since my X, so let me call this X1, Y1, Z1. So this is X1, Y1, Z1, X2, Y2, Z2, X3, Y3, Z3. So since my Z1, Z2, Z3s are aligned, X1, X2, X3s are aligned, Y1, Y2, Y3s are aligned, that solves the computation. Yeah.
Do you have any advice for making three bodies very legible in terms of like drawing all like the coordinate systems on there? Have you recommend like different colors or just drawing it really large, something like that,
You want
to make it easier to read, for example, on like an exam or something? Or not for this class, but
all exams, or there is no exam as a matter of fact in this class. So I don't think you'll, but uh, you can use whatever techniques that you want to use. Usually I use iPad and then I actually use different colors.
Okay.
But whatever works for you, that's good. As long as you know what to do, you should be okay. All right. So we have RRP, and now I want you to tell me, is an important question. My theta 1, is it positive or negative? It's positive. Theta 2 is positive or negative? Positive. That's why I defined like that. And my Z or my X, basically O to B in this particular case is also positive. Yes.
So, sir, the second L2,
Mhm.
shouldn't we count the theta 2 from like, first we align L2 with L1 in the same direction. And then it's like, from that 0, it's like negative theta 2.
Okay, there is a reason for that. I tell you, there is a reason for that.
L1 is something like that, and then it's like something down.
Okay, so let me understand. Whatever I have done, is it clear?
Yeah.
Okay, and bear with me for a second. There is a reason I'm writing it like this, because you are never gonna get a nice, clean representation that is 2D, and you will never get the joints with respect to the base frame. What will happen is you will see something like this. This is called as the kinematic diagram. And this is how the real robot would look like. So if I ask you to do a forward kinematic analysis or inverse kinematic analysis, I will never ask you to do it onto this planar robot, but I will ask you to do this in this three-dimensional robot. However, if you were to flip it or look from top, and then you will realize that what I have drawn here resembles what I have here, except I don't have this dimension. I don't have this dimension. Are you with me so far? What robot is that? That robot is a variant of Skera robot. So once I know how this three-dimensional representation, once I squash this, becomes a slider crank, that gives me an intuitive way to check my equations. Like, hey, I got this fancy equation. If I substitute those vertical distances is equal to 0, I should be getting that very simple equation. Now, there is something that I really want to talk about. Whenever we are actually dealing with robot kinematics, the joint angles are never specified with respect to a reference frame. Joint angles are specified for their individual position. So what I mean by that is you are going to have theta 1 and you are going to have theta 2. And now what you want to do is you want to find out this distance like this. And I would represent what I have shown over here, and that will answer your question. This is L1, this is L2, and this distance is L1 cosine theta 1 plus L2 cosine theta 2. Are you with me so far? Things will get clear once I actually work out an example. So let me assign the coordinate systems. Now, yeah,
Is there a reason you have positive x on it this way? Could it be the other way?
yes, that could be other way too. But then if you're positive x in other way, your z needs to go inside.
Yeah.
So now what I want to do is I want to assign the coordinate system. This is a very, very important exercise, and I'm going to solve about 10 or 15 problems. And I will repeat this before I work out every problem. Because if you assign the wrong coordinate system, you won't be able to solve forward kinematics. You won't be able to solve velocity equations. You won't be able to develop the Lagrangian and dynamic equations, and entire problem would go wrong. So coordinate systems are super important. There are 3 rules, and basically the same rules that get converted into the 4 rules that are required for DH parameters. Just to be clear, I don't like DH parameters, but everyone else loves them, and I'll tell you the reason why. I don't like DH parameters because they are, to me, it's like more mechanical. It does not bring in the intuition. And unfortunately, I can give you the cases in this class where the DH parameter approach does not work. So then they come up with modified DH parameters. And then they come up with exceptions to DH parameters. So what I'm going to do is I'm going to give you a very straightforward recipe that is not discussed in any of those textbooks to solve forward kinematics problem. So please pay attention. First step is assign the coordinate system. And there are 3 rules. The first rule is the z-axis of each coordinate must pass through the joint. So what I'm going to do is, this is going to be my z1. This is going to be my z2. And this is going to be my z3. Everyone understood this? X-axis has to be perpendicular to the z-axis. So, and it not only needs to be perpendicular to the current z-axis, it needs to be perpendicular to the previous z-axis and should intersect. Once again, and I will right now, I just pay attention how I draw the coordinate system. I will work out this problem again step by step. But what I want to do is, I'm trying to convert this 2-dimensional figure into this 3-dimensional figure. So next, there is no Z0 before this. So there is no frame. Z1 is my first reference frame. So, or I can call this a 0th reference frame. This is my first reference frame. This is my second reference frame. So there is no 0 minus 1. So I'm going to draw something like x0 like this. Next, x1. X1 is where the things become complicated. So let me write down the first rule. Z must pass through joint. And I don't have any preference whether the Z goes up or Z goes down. Or in the case of the prismatic joint, which is at the end, whether the Z goes towards right or Z goes towards left. So this is R, P. So yeah.
So when you talk about C must go through the joint and then along the axis of revolution.
Axis of revolution. So yeah, must. So basically, axis So for prismatic joint, there is no axis of revolution. It has axis of translation. Axis of revolution or translation. Second, and this is the important rule. So xn must intersect Zn and Zn minus 1. And it will take some time to get used to this rule. But what that means is, if I want to draw x1, I have two choices. I can draw x1 like this, right? This could be a potential x1. Agreed? I can draw this x1. So which one should I choose? No matter which one you choose, the criteria is this x1 should be perpendicular to z1, because that's a triad. And this x1 should intersect z1 and basically z0. So let's think about it for a second. And I want, let me spend some time over here. So please pay attention. So if I choose, for an example, if I choose this as x1, if I choose this as x1, my question to you is this x1 intersecting, cutting with z0? Yes, no, yes, no. It depends upon where you visualize that joint is. But if you consider the kinematic position, something like, let me draw a 3D diagram. Yeah, so now you will realize the fun with robotics. So if I assume that this second link is something like this, what you have is your x1 is coming in this direction and your z0 is over here. So they are no longer intersecting. However, I want you, in the current configuration, if I were to choose this as x1, do you agree with me? I know for a fact that in this kinematic diagram, my x1 is perfect, my x2, no, x1, sorry, my x1, this is z1. My x1 is perpendicular to z1 and also intersecting with z0. You agree with me? Okay. Now the last part is wherein what do I do with x1? So this is my z2. So I need to come up with x2, and I have again two choices. So one choice is I can use my x2, something like this. The second choice is I can use my x2 like this. Now, unfortunately, for this particular configuration, you will notice whether I choose x2 in one configuration or the other, it is perpendicular to z2, but it's not perpendicular to z1. So this is an exception to the rule, and I will tell you how to take care of problem like this. But what I want you to understand is these rules must be followed for appropriate kinematic diagram so that we can perform the forward kinematics and inverse kinematics without any issues. And the last rule is now we should construct the triad. So construct triad using right hand coordinate system. Now, I just want to be careful here. There is an exception. It's not a big issue, but we will deal with it not in the first class, in next few classes. So if I want to so what I'm going to focus on is I'm going to focus on the first revolute joint and the second revolute joint. So x0, then I have z. So can you see that my y0 needs to go out like this? Then I have x1, I have z1, so my y needs to go out like this. And I'm not going to construct the triad for this, is because as you can see, my rule number 2, unfortunately, is not currently satisfied. Satisfied. For prismatic joint. So what we have to do is we have to add an auxiliary coordinate system that will solve this issue, but we'll worry about that in the next class. Right now, for practical purposes, I have assigned the coordinate system to this robot, which is the planar robot. If this robot get converted to a spatial robot, which means it has 3 degrees of freedom x, y, and z, this is how the coordinate system should work. So again, these rules I will specify again and again and again and again and again and again for all the forward kinematics problems that I will solve in class.
Triad.
Triad means 3 vectors. So let me put it this way: 3 unit vectors perpendicular to each other.
So each joint has its own triad? Is that
Yes.
okay? That's what we've been drawing.
Yep.
The whole time.
All right, but the only thing that I did not talk about here is what is a unit vector. And let me tell you what is a unit vector. So a unit vector only has direction. It doesn't have magnitude, in the sense that it only has unity magnitude. So for an example, if you have a coordinate system x0 and y0, by the way, the stuff that I'm going to discuss now is super duper important, so please pay attention. So if you have a coordinate system that has x0 and y0, if you travel 1 unit distance in the direction of x0, you have traveled I0. And if the hat indicates, that's a vector. It has magnitude. So what is a vector? Has magnitude, and direction. Once again, the stuff that I'm discussing now is super duper important. So which means if you travel by 1 unit, you have traveled 1i. If you travel by 2 units, you have traveled 2i. If you travel by 3 units, you have traveled by 3 I0s. Same thing with y. Y is J0. Travel by 1 unit, 1y. Travel by 2 units, 2j, travel by 3 units, 3j, and etc. etc. So every point in this space is defined by a unit vector and the magnitude associated with it. What do I mean by that? So for an example, if this is the point, this is O, this is point A, this point A coordinates are 2. What did I make a mistake? 2, 3. So then this vector OA is 2 I naught plus 3 J naught. Are you with me so far? Now this unit vector, and this is super important, this unit vector is I naught, J naught is a unit vector, and I'm multiplying this by a scalar number 2 and 3. That is the magnitude. If I want to find out the magnitude of this vector OA, as you know, it is also called as the norm of the vector, or the absolute value of the vector, or the magnitude value of the vector, is square root of 2 square plus 3 square. Do you agree with me? Now, what I want to do is, if I want to find out, this is the question, and this is an important question. Find unit vector in OA direction. If I want to find out the unit vector in OA direction, I'm gonna call it an n hat. This is the unit vector in OA direction, and n hat is equal to OA divided by OA. Are you with me so far? Now, what I would do is, what does that mean? It means you are in the tech center, you want to go to student union. Here is what I would say. I would say, go 5 units each, and then maybe 7 units south or north. So 5 and 7. Or I can tell you, orient yourself in the direction of the student union and walk the diagonal distance. Everything means the same. So the unit vector is telling me about the orientation. Everyone understood this? So if I'm at the right orientation, if I just given the distance, then I just track that distance, which is a scalar quantity, I would get to the destination. Everyone understood this? Are you guys sure? Yeah.
That's when the unit vector is the length of 1.
Yes, unit vector is just length of 1. Magnitude is 1. All right. Now here comes the fun part. What I'm going to do is, I'm going to substitute the values. So these values are going to be OA. OA is, I'm going to write this slightly differently, 2IO plus 3JO. Are you with me so far? And again, at the end of the day, we are dealing with this unit vector n. Divide this quantity by square root of 2 square plus 3 square. Agreed? Divide this quantity by square root of 2 square plus 3 square. Everyone okay with this? Now, what I'm going to do is, I'm going to write this something like this. 2 square plus 3 square I naught plus 3 divided by 2 square plus 3 square J naught. Now you say, what is that? Simple math, right? But now I want you to look at the same equation from a slightly different perspective. And that perspective is, I'm going to define the angle between the vector and the reference. So angle between the vector and the coordinate frame. So this I'm going to call as theta x. Are you with me so far? And I'm going to call, you may say, why are we doing this? But I'll tell you in just a second. This as theta y. Again, in this particular case, theta x and theta y are 90 degrees. So theta 1 plus theta y plus theta x is equal to 90 degrees. But this beautifully converts this equation into something like this. Cosine of theta x plus cosine of theta y. And in case you are wondering what this is called as the direction cosine. This is also called as the direction cosine. Now, some of you may say, oh, great. So what is the significance here? The significance here is once you know these angles, it's very easy to go from one reference frame to other reference frame. And this is called as the coordinate transformation. So the next obvious question is, we are dealing with three-dimensional case. So is there something general rule that can be used to perform so-called coordinate transformation when we are dealing with a three-dimensional coordinate system? And the answer to that question is yes. So what I'm going to do is, I didn't actually draw this, but what I mean by that is, let me show you something like this. This coordinate, if I were to draw a vector, a unit vector, which is perpendicular to n hat, which is m hat, then this coordinate transformation gives me means to get vectors in x0, y0 coordinate frame and transform that to maybe m hat, n hat coordinate frame. And why is this required? Once again, this problem is probably not appreciated much at this point, but I want to emphasize on it. So what that means is, I have a point, and that point, as you can see, is point A. That point A has the coordinate 2, 3. What that means is, if I travel 2 times unit vector in x0 and plus 3 times the unit vector in y0, which is j0, I get to point A. But the question I'm posing is, I still want to go to point A. I still want to go to point A, but I don't want to use the coordinate system x0, y0. I want to use the coordinate system m hat and n hat. What should I? How should I travel? In this particular case, it's super simple. You would simply say, oh, no big deal. Just travel square root of 2 plus square 2 square plus 3 square square root. Take that distance and travel in the direction of n hat. Do you agree with me? What we did? We actually did a coordinate transformation. So A is given in the x naught, y naught coordinate system, but with this coordinate transformation, in this particular case, it works out very simply. You actually express that same coordinate in m hat and n hat coordinate system. Here comes the critical point. Now I have some other point, say point B, which is at 3, 2. I have another point, which is at 3, 2, and I want to express that 3, 2 coordinate point in n hat and n hat coordinate frame. And this coordinate frame is fixed, not rotating. So basically, these two coordinate frames are right now fixed with respect to each other, but that point A has moved. What should I do? And that is where a generalized coordinate system transformation would help. And that is coming next. And coordinate system transformation and these 3 rules. Once you master these, you can solve any forward kinematics, any inverse kinematics. As a matter of fact, you can solve, you can start. We finished 3 chapters from your textbook. So, but let me set the stage. Why is it required? Why all this jugglery with coordinate system required? Because please try to understand. We have 3 joints. Each joint has its own coordinate system. There are multiple links. Each link is represented in its joint's coordinate system. What that means is, if you look at the first horizontal link, that is conveniently expressed in x0 and y0, z0 coordinate frame. If you look at the second horizontal link, if you were to look at this, which is L2, that is conveniently expressed in x1, y1, and z1 coordinate frame. So you cannot add dollars to pesos. You cannot add dollars to pounds, dollars to dollars, pounds to pounds. So before you do anything, everything has to be in the same coordinate system. And that is where coordinate transformation is required. Everyone understood this? So how does this coordinate transformation works? The technique that I'm going to teach you is not discussed in any of the textbooks. Okay? But I promise you, this is the most intuitive way to understand coordinate system. And if you don't believe me, just after this discussion, just go on to Wikipedia or pick up any robotics book and just try to read coordinate transformation and rotation matrices. And then tell me what you think of the technique that I'm going to discuss now. So everyone, please pay attention. So let me set the problem. And this problem is a simple problem. I have this coordinate system. I'm going to call this coordinate system x0, y0, and z0. It's a triad. Everyone look at the board. I'll give you time to copy it down, but I want you to understand this concept to the core. Because once you understand this, robotics will be a piece of cake. First 3 chapters done. Okay. Now what I'm going to do is, I'm going to look at a positive rotation about z-axis. So positive rotation about z-axis is theta z. So once I perform this positive rotation about z-axis, you agree with me, my new z1 axis will coincide with my old Z0 axis. Do you agree with me? However, my new X1 axis will be somewhere here. And again, its perpendicular brother is going to be here. You agree with me? This is how it's going to be X1 and Y1. Okay, now what I want to do is, I want to come up with this rotation matrix. Rotation matrix is this 3 by 3 matrix. And then if you follow any textbook, they will draw the perpendiculars, and then they will try to find the resolution and so on. But what I want to do is, I want to give you a very simple technique. So this has 9 blanks. 1, 2, 3, 4, 5, 6, 7, 8, 9. So what I'm going to do is, I'm going to say here projection of and this is basically the new axis, which means this is going to be X1, Y1 and Z1, because that is the rotated frame. So my initial was my old coordinate frame. So I'll write what I mean by old. My old is X0, Y0, Z0. My new is X1, Y1, Z1. So projection of X1, Y1, Z1, and this is projection on. This is old. And old is X0, Y0, Z0. Are you with me? Let's start with the easiest part. Z1. What is the projection of Z1 on Z0? 1. Right? They're aligned. What is the projection of Z1 on X0? What is the projection of Z1 on Y0? 0. Agreed? Now, whenever you have something like this, 0, 0, 0, clearly you have zeros in the other column, other row. So basically, if you have 2 zeros and 1, wherever there is 1, the rows that contains 1, the column that contains 1 will have zeros. Are you with me so far? So now I'm left with filling these 4 blanks. But I'm going to use the same approach. And I will do it step by step. So let's look at X1. Draw a vertical line. So now my question is, if this, do you agree with me? This is theta z. Projection of X1 onto X0. Projection of X1 onto X0. I will show you. This, can you see that this is cosine theta z? Agree or no? Okay. Then since this is the resultant, this is the other projection. Projection of X1 onto Y0. Can you see that this vertical guy, this is the projection. I need to be super duper careful, at least for the first problem. This guy is the projection here. This guy is the projection of X0. So what is projection of x1? What is the projection of x1 on y0? Sine theta z. S theta z. Are you with me so far? And why it is positive? Huh?
So with sine of theta, you in the x1 direction. No, I want to the y.
Enlightenment. Wait for it. The stuff that is coming to you next is legendary. So, so why? I'm serious. I'm not kidding. Y1. Let's do the same thing with y1. Again, to do that, what I need to do is I need to draw a perpendicular. So can you see I draw a perpendicular from here? So I will draw perpendicular from here. And now projection of y1. I'll start with the easy part. You agree with me that this is theta z. Projection of y1 onto y0. Projection of y1 onto y0 is positive cosine theta z. Yeah. Yeah. Right? Everyone agrees? Now, please understand, this is the resultant. So this guy should be like this. So the projection of y1 onto x0, projection of y1 onto x0 is and friends, this is the rotation matrix. So whenever you have determination of rotation matrix, always remember this. What you have here is the new coordinate frame. What you have here is the old coordinate frame. And you would be always looking at projection of new coordinate frame to projection on old coordinate frame. Everyone understood this? As a matter of fact, we are pretty much done because this is the most important coordinate frame we will use to solve all forward kinematics problems. Why? Because rule number 1 says the axis has to pass through the joint, which means all my rotations are always going to be about z, which means the only coordinate transformation that I should be remembering is this. Right? As a matter of fact, I can actually write the homogeneous transformation and solve the forward kinematics problem right now. But you don't realize the amount of information that came to you. So I will let that sink in. So if you don't believe me, go open, just jump onto the 3rd chapter from your textbook. That's what it is. Anyways, that being said, what I want to do is, just for my sake, to complete, I want to give you the coordinate transformations for the other coordinates. So now if I have the rotation about maybe y,
Does this transform have a name, the one we just did?
we can call it Rydberg's transform. Oh, did I tell you Rydberg's let me see. Rydberg's corollary to Newton's second law? No? Okay, so I think that is important. Can someone tell me what is Newton's second law? Force is equal to mass times acceleration. Force is a vector, mass is a scalar, A is a vector. This is Newton's law, right? So which means force, I can write Newton's law in simple words, something like this. Force causes acceleration. What is the Redcar's corollary to this? Redcar's corollary to this is sometimes force is not enough. Sometimes force is not enough, and what you need is you need some type of jerk to get the things moving. Think about it. Sometimes even if you apply force, things don't move. What you do? You take a hammer and hit it. What are you doing? Derivative of force, derivative of mass, again 0. Basically, it's a constant, m comes out. You have derivative of acceleration. So what is derivative of force? Impact. What is derivative of acceleration? Remember this. Sometimes in life, force may not be sufficient and you have to be a jerk. Or you have to use. So, jokes apart, notation about y. So if I rotate about y, my y1 is going to be like this, and I'm going to have a rotation like this. I'm going to have a rotation like this, and I don't know if I mentioned this explicitly. These rotations are positive. That's why I have cosine theta, sine theta, sine theta, cosine theta in this structure. So the question here is, what if the rotation is negative? No change. Only thing is, instead of positive theta, substitute negative theta. And remember this relationship, cosine of negative theta is still cosine theta, but sine of negative theta is minus sine theta. That's it. And whether the rotation is positive, negative, doesn't matter, you can take care of it. Okay. This is theta y. This is theta y. And you know what? I'm going to solve the hardest problem here, and I will let you answer the easier part. So what goes on top? Projection of x1, y1, z1. What goes here? Projection on. And I have x0, y0, z0. I will solve the hardest part. Can you see the projection of y1 on y0 is 1, which means there will be a 0 here, there will be a 0 here, there will be a 0 here, there will be a 0 here. Because all the columns and rows where there is 1, they have to be 0. Which means you have to now tell me what are these blanks. Projection of x1 onto, okay, I need to give you, this is x, this is x1, and then this is going to be c1. Projection of x1 onto x0. Projection of x1 onto z0. So if you have a little bit difficulty in understanding, I'll draw the projection so that will make sense. Sine theta y. Projection of z1, and I need to draw this correctly. So So projection of Z1 onto Z0, cosine theta y, and projection of Z1 on X0 is sine theta y. Yeah, so let me try to draw this properly. That way, this needs to be sort of parallel to this. But still it doesn't look parallel because the way it is drawn. So, but I think you got the point. So this is rotation transformation. And the last part is the rotation about X. And what you would see is they would get flipped. And I will work out these transformations again in next class. I will explain these 3 rules again in the next class. And then I will give you the expression for homogeneous transformation. And then we just solve problems. I'm going to stop here today and I will see you on Tuesday. Yeah.